So I try to pick some different functions from what we did the previous class. But the key we want to make sure is go through and like, hey, any type of function I get, let's sit down and look at what we have to do to go through the process of differentiating. Okay. So dealing with f of x here, what do we have to be careful of when we're trying to find the derivative of this? Trying to find f prime of x. Anytime we have parentheses involved, which rule are we going to have to use? Well, might have to use, I should say, not going to have to. Chain rule, right? In this case, we need the chain rule. Now, we can avoid it by going out and simplifying this if you wanted to, right? You can go find the trinomial that's associated with this, so you avoid the chain rule. But hey, guess what? The chain rule here is not that bad. You just have to remember, hey, this will be 2 times the 3x minus 5 raised to the 1 as an exponent. Doing the power rule on the outside, we just have to make sure to multiply by the derivative of the inside. Since the derivative of the inside here is just 3x minus 5, the nice thing about that derivative, it's just 3. Any questions where we're getting that from, though? Or getting 18x minus 30 from? Now, keep in mind here that the notation is very important. That's one thing I've stated probably a lot now, is just always watch your notation. What happens is oftentimes on a test, it becomes just little points because of notation issues, but it can also lead to something being wrong if you don't have it marked correctly. So that's why we definitely want to be careful. Okay. What we're going to see here, and one of the things that we're going to kind of work on is, like I said, I think my plans for Friday is to give us a little like project to work out that we'll work on, get started in class and work on our own. But it's going to start bringing the different perspectives together. So as we deal with finding derivatives, don't forget about, hey, when we deal with the rates of change, right, it led to derivatives. So we need to remember that from a slope perspective. But we're also going to talk about, like, you know, why in the world would I want to go do something like this now? Right. So as we deal with that, we can now treat the function, the derivative function, as its own function for purposes. Now we'll dive into like interpreting first derivative, second derivative more after test 1. But right now it's about making sure we can do the derivative and making sure to kind of differentiate between the derivative and the original function. That's one thing I would say there. Okay. Any concerns with this first one, though, I can help someone feel better about? All right, so let's go to the second one. We're trying to find g prime of t here. Now, this one was a little bit different than some of the other ones. Hopefully what you'll see here, though, is when we go to differentiate this, make sure you see we're doing it with respect to t now. That's our input variable, is t. Also see that here you can separate this into 2 terms. So this would be using the sum of difference rules to help us out, would definitely be helpful, okay? So as we look at this one here, the first term, hey, I have a fraction, I'm going to differentiate it. The second one is 5t cubed, so just making sure to use the power rule in the t cubed, okay? But make sure you see here, I wrote the differential part a little bit different because our input variable is no longer x, it's t, right? So when we're doing this, we're saying, hey, my derivative is now with respect to the variable that I'm focused on, the t. With that said, if I came over here and said d dx and I put like 2t minus 3, what would that equal if you don't have an X there? It would just be zero, right? Understand at that point, any other variable is treated like a constant in a sense. So you have to be careful with how you write something. Okay. The only exception, we'll talk about this, is going to be like, say, Y, because Y would be our independent variable. So that's where you'll see some differences. So like if Y equaled 2t minus 3, we would say, hey, dy dx, because we can differentiate the Y, equals 0. Okay, but that'll be one thing we kind of go in as we go through the rest of the course here. So it's always important though, as hopefully what you'll see here is be careful on what you're writing and how you interpret what you're writing. Okay, we don't want to put d dx here because now I'm dealing with t as my independent variable. You mean put the 5 inside the parentheses? Yeah, nothing's wrong with that. I was just showing that, remember constant, multiple, sum and difference. That would kind of like what we did with limits. The same thing applies here. Okay. The focus of that one will just be the t cubed. The first one, though, we have a fraction. So how would someone prefer to differentiate this one? Or how should we do it? Anytime you have a fraction, what rule should we be thinking, hey, I probably need to use this? The quotient rule, right? Now, do you have to use the quotient rule? Not necessarily. Okay, so if you wanted to, this is one thing I would like encourage you on your own time is go differentiate this and see if we get to the same thing. The one thing I will say is when you do it in this focus, you're going to be using the product rule instead, which will give you 2 terms rather than 1. So that'd be the big difference is, hey, I'm gonna probably have 2 fractions rather than 1 fraction. So if I get the common denominator, we would get these 2 to then be the same. Okay. But I encourage that because maybe you're on the test and it's like, okay, I remember the product rule, but I can't remember the quotient rule right now. Even all that studying I'm doing, make sure you know how to get different perspectives to work through something if you get stuck. Okay. With that said, though, it doesn't matter which way we deal with it. We're going to look at each one individually as far as the numerator and the denominator. Okay. So are we good if I put the derivative of t is 1 and the derivative of 3 minus t is -1? Is there any concerns there?
Why didn't?
Right, because we're dealing with something that has 2 pieces to it, right? So whether it's division or multiplication, we have to look at them separately first. And then we're going to build everything together through the quotient. Okay.
Yeah.
Are you good though with those derivatives themselves, meaning from the numerator and the denominator?
That's why it's plus 1 negative.
Yeah, so nothing's in front of this t, right? So hey, when I do the derivative, it's 1, but be careful with this one because it's minus t. That's why it's -1. Okay. Where'd the 3 go? Sorry, it wasn't supposed to be me erasing it, but so make sure you see, hey, the 3 was constant, so that's gone, but that negative is still important. Okay. Now, as far as the quotient rule tells us, now we have to go in and say, hey, we want to do low d high minus high d low all over what? Low squared. Good. Is that all our derivative? Yeah, don't forget the fact that we had 2 terms here, right? The whole quotient, well, that was a lot for one step, but hey, that was just one of the terms, right? I need to make sure to go over here and write, hey, plus 5 times 3 t squared. And please understand that, like, here I'm writing this as 5 times 3. If you already knew it was 15, you don't have to write 5 times 3, okay? I'm just making sure everyone sees that the 5 was already there and I brought the 3 from the derivative, okay? As far as written work is concerned, this to me would be a step that everyone probably should have. Because you're writing out the quotient rule. When it comes to dealing with a term like 5t cubed, as mentioned, if you would have left a 5 inside, doesn't make a difference to me. You didn't even have to write it this way. You could have went straight to the derivatives. Okay. I just wanted to make sure to stress that, hey, that plus sign means I have to do two separate different derivatives here for the two terms. Okay. Now, thankfully here, the multiplication is not too bad. The only thing you want to be careful of there is that the t's in the numerator do cancel out. If the watching your signs and how that kind of works out here, that's definitely one thing kind of sneaks in. For those who like, as you're looking at this, I know we kind of started the quotient rule this week. Please understand that practice is where this comes into. I'm like talking to my online class as well. Just remind them like this is something, if you don't sit down and practice it, of course you're not going to remember the rule. How many of you have taken a calculus class before? So this is something new to you, right? This isn't like algebra where you may have seen it before taking college algebra, right? This is something that's new, so make sure we're practicing. The one thing I will say is be thankful you don't have any trig mixed into it. Just algebra. Of course, if you're interested, let me know. We can get you ready for the 5-hour class. Is there any questions or concerns with this one before we go look at that third one? I'm hoping that, us walking through and have more kind of group conversations Monday helped with this. I wanted to try to get some of the different problems in that. This was one of the ones I was trying to get to Monday. We ran out of time. So any questions or concerns though before I go to the next one? Everyone's got this one? All right, so here's another one. Now, as you finish writing this one down, what are some things you would have to be careful of with this one, right? Can you take the negative 3x squared and distribute it inside the parentheses here? No, right? Because there's an exponent, right? So make sure we're watching for stuff like that. Would we want to try to simplify this one and then differentiate it? Would that process be fun to multiply 5x plus 1 with itself 5 times? No. So understand this is making us use what? Not, well, we're going to have to do a chain rule problem, yeah, but understand this is forcing us into the product rule, right? I have to use the product rule with this one, unless I want to spend 30 minutes writing that out. You could definitely multiply that out, but just know you're adding more work. If this was a test problem, it wasn't designed for you to simplify. It was designed for you to use the product rule. Now, as far as like a chain rule situation, always watch for the chain. That's a tough one as we deal with the chain rule. It's not something, there are some problems that, like the first one, it's like, hey, that was just a focus of chain rule. But here we will need a chain rule. With that said, though, we can go take the derivative of them individually. Taking the first factor, negative 3x squared, let's differentiate that. And then the second factor. Okay, so what would you guys put for the first factor here? Is everyone comfortable with that one? And again, as you saw in the last one, I put 5 times 3. If you need to put that, just like I did here, if you need to write this out, make sure you write it out for what you need, okay? Over here, though, this is where we have to be careful, right? Specifically, the fact is what's inside. There's a 5x in there, okay? If it would have been just x plus 1, technically we can get away with not doing the chain rule, but it's always good to just kind of realize it's not just x to the 5th, right? I have 5x plus 1 to the 5th. So when you deal with this one here, this is going to be the area where you're like, hey, I do need the chain rule for this piece. So the 5 that's in the front here, that's coming from the power rule. Hey, bring down your exponent and then subtract 1 to get your new exponent. That's weird.
One.
You talking about the first one or the last one?
That's
All right. Why did I do the last one? Where did that come from? So this 5, remember, as I was just stating, is coming from the power rule. I'm bringing this 5 down, right? And then 5 minus 1 is where the 4x come from. Okay. Now remember, we have parentheses here. So what do I have to do to this that gives us 5?
oh,
Now they're both 5. I was getting there. I'm sorry. I thought I was gonna get interrupted. But what's happening there is that's where the chain rule kicks in that says, hey, I have an extra 5 because I had 5x plus 1 on the inside. So like a more expanded way to write this would be 5 times 5x plus 1 to the 4th times the derivative of 5x plus 1. Which I would definitely, if you need to see that, make sure you write it that way so you can see like, hey, I got the 5 because derivative of that. Does that help?
yeah.
Okay. Now writing that, excuse me, writing that in a simplified form, that gives us what, 25 times 5x plus 1 to the 4th as an exponent? Any questions where we're getting this from before we go to the next step? Now, what's the difference that we have to be careful of here, right? Remember, quotient rule, we subtracted, but the product rule, what do? We add them, right? So as we go down here, we're going to say, hey, I'm now trying to find the derivative of the whole function, g prime of x now. So we're going to do first times the derivative of the second. Plus second times the derivative of the first. So make sure you see here, we still have 2 terms involved. I have my first factor, I have my second factor. But it's kind of alternating, right? So the derivative of this gives me the second part here, or the derivative of that first factor is what gives me the second terms piece, right? First times the derivative of the second, plus second times the derivative of the first. Now, as far as cleaning this one up, the main thing that I would say here is understand we definitely don't want to multiply out those exponents. Okay. So the main step that you definitely want to focus on is, as you see here, multiply the pieces that you can. So like, hey, I can multiply these two. I could just multiply this with that plus 1 there. So all that change was, instead of a plus, now we have subtraction. Okay. With that said, from a simplifying perspective, we're in a good place here. Okay. So for this test, if I just say find or differentiate the following or find the derivative function, I feel like this is a good place. Okay. Now, as far as moving forward, so this next piece I'm just going to show is just kind of like, hey, this is something we can do with this. All right. Looking at these two terms, what do they share in common would be another question, right? So oftentimes, if I want to go further with this to say, like, when does this derivative equal zero, having a factored form is much nicer. Okay. Well, hopefully what you'll see there, they both have an x. 75 and 6 are both divisible by 3, and they both have that 5x plus 1 there. Okay. So we can rewrite this function using factoring. We can say, hey, let's sorry, I'm going to factor out a negative 3x times 5x plus 1 to the fourth. Only pulling out 4 though, because both terms share 4. Take the smaller of the exponents, but then you got to multiply with what's left over. So this would be what? 25x times, not times, sorry, plus 5x plus 1. Nope. 2 times 5x plus 1. Okay. Now, understand here, this is like if I asked you to do more. The reason you'd want to do this is if I'm asking you, then go find when does this derivative equal 0? Hey, I can find some nice steps with this process. Okay. What you'll see here is now we have this to where I have 3 linear factors here of this function. This one needs to be simplified itself, but no exponents are involved anymore, right? So it's a linear factor that just needs to be simplified. Okay. If we do simplify that, that would be what, 35x plus 2? But please understand, like for this particular test here, unless I ask for this, don't go do extra work. Okay. Now, the next test, be prepared for that to be a question. Okay. Is there any concerns though with stopping here and knowing when to go forward? Any questions, concerns with the overall problem I can help someone with? All right, so moving forward, then the next step in the process is to understand that as we take derivatives of functions, as long as you have a function that's continuous, you can continue taking derivatives of it. Okay. When we deal with different types of functions, like we saw here, yeah, we took a derivative of it, but make sure you remember, like, we're kind of taking into account that we're ignoring the 3. Why are we ignoring 3? What does that do here if I try to plug in the 3? It puts a 0 there. So at some point, we would have to discuss, like, hey, I can take a derivative of it, but at some point, we got to acknowledge that I should not be using 3 here, right? There's a vertical asymptote at that point. Okay. Or there could be a vertical asymptote, I should say, at that point. All right. Here we have a polynomial function, right? So we wouldn't have to think about it, right? Hey, it's continuous. I take a derivative, I can move forward, we're good to go. All right. Well, here's another function then. Let's look at it from this perspective. Now, what I want you to see here is as long as I have a function, I can differentiate it. I can find a derivative of it. Okay. So whether the function is considered a original function or a derivative of another function, we can take a derivative of it. Okay. At some point, though, the side note there was at some point we deal with the discontinuity. We do have to discuss that. Now, as far as what you're going to see here is moving forward, we have to be prepared for the 2 different notations, right? So we looked at function notation. Here's our Leibniz notation. What you'll see here, though, is this is what we're going to use to represent not the first derivative, but the second derivative. So what you're seeing here is like, hey, d dx of dy dx. I have a derivative, and I'm going to take another derivative of it. Okay. Based on how we write derivative notation with this, right? What you'll see, they kind of just follow the fact that, hey, we would write dx twice, and we would write d twice. So that's where they're superscripts. They're not necessarily exponents here. Please keep that in mind. Okay. What you'll find is though, is I'm gonna take this problem and I need to find a derivative of it by differentiating both sides.
Did you get a message? It's
Uh-uh.
not just on Canvas, right?
Okay, I'll check it. Thank you. All right. Now, a lot of times on the left side, please understand that we're just gonna write what this is, but I just want to make sure to show you that like, hey, this is the long step, I guess you would call it. Because over here, we would just say, hey, this is dy dx. Y was given to me as a function in terms of x, so dy dx represents the derivative of that original function. All right. Over on the right side, though, I chose a quadratic because, hey, we know it's continuous. I can take a derivative of it. Well, guess what? The derivative we get from this will be linear. I can take a derivative of that. So as far as this first derivative is concerned, what would y'all get?
2x negative -6.
Good. Do we want to put anything else?
That's it.
Because the 5 goes to 0, right? So the key, always watch those constant terms. It's easy to accidentally bring a constant term when you're not supposed to, right? So always be careful there. Now, as far as this is concerned, this is what we would call the first derivative. Okay. When we deal with this first derivative gives us the rate of change of my original function. Right? So if we came over here and said, hey, let x equal 5, well, what we'd get is dy dx equals 4, right? So the rate of change when x is 5 is 4. If we go to the original function and we plug in 5, that'll give us what? 0. Pretty great random guess there, right? The idea from the original function is a position, right? That, hey, when I plug in 5, the position is going to be at 5 comma 0. If we look at that from a graph standpoint, this is why we like tangent lines, right? There's a tangent line that helps us represent the rate of change at that point. The one thing we would say here, hey, the rate of change at that point is going up by 4, okay, for that instantaneous rate of change. Well, if we go over here now and take a derivative of this, what we're trying to get to is how is the rate of change itself changing? All right. Now, what I hope to do Monday with you is make sure to go through some application problems that help visualize this. But a great application problem for this is talking about, like, say you're driving down the street in your vehicle. Okay. Different perspectives of that is your position is changing, right? You're going from one location to another location. So we can measure the distance that's been traveled in that perspective over time, right? Now, is your distance always changing at a constant rate? Well, the answer is going to be no there, right? Because sometimes you got to stop at a stop sign. Sometimes you got to stop at a light, right? Well, that means your rate of change is not consistent through that function. Well, even when you're dealing with that, right? You're not traveling at 30 miles per hour every single time you start moving, right? You're not going from 0 straight to 30. Okay. There's an adjustment that we call acceleration there, right? So you have a velocity that you travel at, right? But then we have acceleration that fluctuates whether you're speeding up or slowing down in that process. This is where the second derivative comes in. Okay. So with this here, are we good with how I'm writing it? That's my first concern. Just the idea here, I want you to see is we can do another derivative. That's the main thing I want you to see. Once I get the first derivative, I can take another derivative. This is the notation we use. If you need ways to understand this, think of a position function, velocity function, and acceleration function. That kind of helps us connect it to something we see every day. Now, as far as the notation is concerned, we found the first derivative and we're taking a derivative of that. That's where the second derivative notation comes in. This will equal, though, just 2. Okay, where I'm getting the 2 from? Could we keep going? We want to take another derivative? We could, right? Now, I only said to find the second derivative here, but let's look at it. Before I do that, though, is everyone okay with where I'm getting the two from? So this is just me saying, hey, even though it wasn't asked, I can definitely go further. So if I want to take the derivative of what was considered the second derivative, how do you think we should write that? It was good that we just put threes there instead of twos for the third derivative. With that said, though, what would it equal here?
Zero.
Very good. Could we keep going? Why not?
Let's see.
Good question, right? What's the derivative of zero? What is it? It's still zero, right? So we could keep going, but it'd be pretty redundant, right? What you'll find is like when working with a polynomial function, it's like if I ask you to find the seventh derivative here, well, it's a degree two, so by the time I get to seven derivatives, it's going to be zero. Okay. Each derivative takes 1 degree away as we go through the process. There's different things where, like, if you were to go higher levels of math, we have ways to deal with that. So if needed. But like from a practical application, we wouldn't need a third derivative if we were talking about velocity and acceleration. Okay, so from a function standpoint, it always depends on what you're trying to do. Okay, what you'll see is once we get done with the second test, we'll jump into describing functions, and the first derivative and second derivative definitely help us out a lot with different problems. Okay. Are we good with the notation? That's one thing I want to take from this. Okay. Well, guess what? We can still use function notation as well. Now with this one here, hopefully what you're seeing is my function notation. We just kind of continue with what we were doing. The number of primes you put tells you the derivative you're working, right? So if I have f of x, the next thing I need to go find then would be f prime of x. That's the first derivative. Right? So taking the derivative of f of x, we write as f prime of x. So then taking the derivative of the first derivative itself, we're going to write as f double prime of x. Okay, so the number of primes will represent the number of derivatives. Okay. What you'll find is this is tough because we don't want to put like, say, 5 prime symbols next to each other. Right. So this would be a situation where the textbook would definitely be something you want to refer to on how they handle it. Because I've seen situations where, like, if I do this, what derivative do you think we're working with? That's a V. That's I was about to make it bigger. Sorry. I figured it was because it was small. If you see prime and then a V behind it, what derivative do you think it might be?
Third.
The third, no. 1, 2, 3, 4, 5. What are those? Roman numeral. Don't use those all the time, right? But understand that some textbooks, they kind of take that same kind of pattern for derivatives. Okay. Not that, again, we're not going to get to the fifth derivative in this class very often. I'm just making sure to point out, like, say you're on the homework and they're like, they give you a fourth derivative and they tell you to find the fifth derivative, right? Because to me, that's a great way to practice this. Hey, here's the second derivative. Go get the third derivative. Know how to write it out. Okay. But that's probably going to be one of those, always check your textbook to see what it says, right? Look at what Pearson's writing so that you follow that same pattern. With that said here, how would someone approach this derivative? We definitely do the quotient rule. Technically, yeah, we would need the chain rule here, okay? This would be one of those problems that you're just gonna be multiplying by one, okay? Now, we already did the quotient rule. So what I'm gonna do is say, hey, this to me is a situation where I can go over here and say, hey, this is -2 times x minus 5 to the what? -1. I like that though, because how many variables does it have? Just the one, right? So at this point, hey, that's a pretty straightforward power rule. Technically, yes, we do need a chain rule here, but what's the derivative of x minus 1? X minus 5, sorry. Since it's 1, the chain rule will always just be times 1 at the end, okay? Now, if you do the quotient rule here, is it wrong? Not at all, okay? So please keep that in mind. If that's where you're like, hey, I know quotient rule, then do quotient rule. The derivative of 2 is 0. You'll see that it works out quite nicely that way. What you'll find is you'll have to just do a little quick simplification. That's it, okay? With that said, are we good if I put this for the power rule aspect? Now, from we had -2 though, right? We multiplied with -1, that's why it's +2. Okay, so it did change. Then I subtracted 1. Now, here technically, yes, we should be saying times 1. Do we have to put that though if we recognize that already as chain rule? But I would encourage you, if you need to be like, I have a chain rule here, make sure you put times 1 to like, hey, I did the chain rule. I definitely did it. Okay. Now, the reason I definitely like a negative exponent here is, do I have to rewrite it to go find the second derivative? Or can I just jump straight into it? If you do the quotient rule, you're gonna have to go do the quotient rule all over again. Right? But this is a situation where you're like, hey, because it was just 2 in the numerator, using a negative exponent can help this go a little bit smoother. Okay, remember, this would be true like if you had a square root in the denominator and everything, just be careful. Your rational exponents. We've done some of those already though. Make sure you see here though, this would just give us -4 times x minus 5 to -3 now. And as we were just talking about other ways to write stuff, this would be a situation where, hey, it could be written as -4 over the x minus 5 cubed. Okay. As far as this test is concerned, I'm fine if you stop there. As far as the homework is concerned, no, they may not allow you to have negative exponents. Okay, so you might have to rewrite it there. Questions or concerns I can help someone with here?
So if we sub there, that's.
Yes, what I've circled, I would feel is, hey, you found the second derivative. Okay. Now, what you'll find is like when we start going into the next steps, writing is going to probably make it a little bit easier for us to discuss. So we would probably rewrite it at that point. That'd be kind of like what I was saying with this one here. Hey, when we need to go further, then we can do the whole factoring part. This to me here, this one's not the same, right? This one, you could rewrite it in 30 seconds, right? Depending on how fast you write. So there's no big deal. Whatever way you want to write it. I'm fine with the negative exponent for the fact that I found my derivative. That's what I was looking for. Everyone follow me on that? Now, one question I have for you as we finish up. How many x minus 5s were in the denominator when we started? How many were there when we were done?
Oh, yeah.
3, right? So what happened to the exponent is we went from the first derivative down to the second derivative. It gained 2, right? 1 with each derivative. Okay. Which will hopefully what you'll see there, it's not polynomial, but it still followed that kind of power rule perspective, right? So whenever you deal with even something that has a little bit more involved where you need to do the quotient rule, pay attention to your degrees, right? That it still kind of plays a part of that. When we were done here, how many t's did we have in the numerator? It's gone. But how many did we have in the denominator? Sorry, factors. Two, right? So it followed that same kind of pattern still, right? Now, but hopefully what you're taking from this is, hey, I can take a derivative of a derivative function. Okay, the notation that we should expect to see is f double prime or more if need be, or the Leibniz notation as we see here, where we had d2y, d squared y all over dx squared. Okay, using those superscripts. Okay, any questions or concerns though as we finish up today? All right. Well, if you don't have any questions, I got everyone for the attendance. So have a good day, and I will see y'all on Friday. Now keep an eye on your